Hi, good day. My name is Jordina Pierre, and this is my presentation on the work that I did during the summer. And the title of my presentation is Simulations through Megalib and GEANT4. So the goal of this project is to develop a radiation simulation that would inform design parameters for the UVI-GREAT mission, which is short for UVI Gamma Ray Experiment for Astrophysical Transients. And this mission is going to help complement measurements of Goddard's own CubeSat. These gamma ray observations will help to better identify potential sources of gravitational waves by pinning down the exact time of the event. And this will help to complement BurstCube because BurstCube does have some limited capabilities when it comes to event localization. And you might be wondering, well, why are we even interested in studying gamma rays in the first place? Gamma ray bursts are the most powerful or energetic explosions in the universe. And we're interested in learning about them because they can help us to learn more about the beginning of the universe, as well as how key elements in our periodic table were formed. So some of the missions that already measure gamma ray bursts are Fermi and BurstCube. And Fermi, formerly known as GLASS, helped to open the door to high energy exploration and help us to learn so much more about black holes and gamma rays and so much more. And so to help expand on that, BurstCube was created. And this is a 6-unit CubeSat that works great, but the only problem is that it orbits the Earth. And because it does this, we don't have a 2-pi field of view or a full view of the Earth, which will help us to capture more events when they occur. So to help counter this problem, or to address this problem, UVI-GREAT was formed. UVI-GREAT is a 3-unit CubeSat, and it will be launched on HASP. HASP is short for High Altitude Student Platform, and it's a program that provides high altitude balloon flights for 12 student experiments. So the operational concept of UVI-GREAT: 2 ways the gamma ray is going to interact with this device is through Compton scattering and the photoelectric effect. And how it's going to work is the biggest or most important part of this project is the crystal, the scintillator crystal. And this crystal is going to help produce the data that we need to actually characterize the gamma rays. So on the left, I have a simulation of what it would look like, but that's not how the scintillator crystal looks in real time. So 2 ways the gamma ray is going to interact is through Compton scattering and the photoelectric effect. And the photoelectric effect is the emission of electrons when light hits a material. So you have your incident photons. In our case, it will be the gamma rays, but in this picture, it's considered to be light rays. And what it'll do is interact with an atom, in our case, the scintillator crystal, and the photons, the incident photons disappear, and photoelectrons are produced and injected out of the crystal. Next, we have Compton scattering, which is the scattering of a photon by a charged particle, which usually is an electron. And so in this picture, we have the X-ray photon. Our case, once again, would be a gamma ray photon, and it's going to interact with the electron, and both the electron and the photon will be scattered in different directions. And as a result of this, the photon is going to lose some energy, which is considered to be called the Compton effect, which is what we have right here at the top. So step 1 of my project challenge was to simulate UVI-GREAT. And in order to do this, we had to use the Megalib software. Megalib stands for Medium Energy Gamma Ray Astronomy Library, and it's the complete data analysis chain from high energy data analysis to just simulation data analysis. And it was originally developed for the Mega Gamma Ray Telescope, but now university students, regular civilians like, well, not me, but I am a regular civilian, can use this software to help further whatever project that may be going on. So on the picture I have attached on the left is a breakdown of the Megalib software, and I circled in the certain applications that were used in this project. We have GEANT4, which is considered to also be called COSIMA, which is why you have the pointers going back and forth between the two. And I also use Revon, which I will explain further in the presentation. So step 2 of this project was to prepare/run Geomega. And Geomega is a detector geometry package that was used in this project to actually simulate the crystal that you saw previously. And in order to do this, a .geo.setup file was first created. As you can see, I have here my Geomega underscore version 1.geo.setup file. And in this file, Geomega allows you to define the density of your model, you can define the visibility, the position, the rotation capabilities. There's so many things that Geomega allows you to do. And when you do come and call or run this application in the terminal, this is the GUI or the GUI that will pop up. And as you can see at the bottom, the file name is different because when I first started, the computer somehow changed my type to a .rtf file, and that caused the whole thing to not run properly because it's supposed to be a .geo.setup file. And this is what resulted. The green rays that you see pointing towards, these green rays you see pointing towards my model, they were not initially there. I placed those there so you can get a visual of what actually is going to happen. But what was produced by Geomega was this pink model, mass model that you see here. And this is our cesium iodide crystal model. Step 4 is GEANT4 or COSIMA, which is what I mentioned before. And this application was used to simulate the high energy gamma ray particles at the simulation model. Once again, in this application, a .source file was first created, and it's one of the requirements, just like with Geomega, a .geo.setup file was first created, a .source file needs to be created. And this is going to be our source, like our radioactive element, like bismuth 207, which is what I have on top here, cesium 137, things like that is what will go into this file. And you can define if it's a monoenergetic particle, if it's a gamma ray particle, certain things like that can be defined, how many triggers you want thrown at it. Everything can be done in COSIMA. So REVAN, which is short for Real Event Analyzer, is the application that I showed before, that is going to produce the data that we want. And how it works, it's going to combine our COSIMA file that you saw before, along with our Geomega file that you saw before, and combine the data from those two applications to produce the charts you see before you. The figure on the left is my bismuth 207 photoelectric peak that was produced, and I compared it to the figure on the right, which is a readout from the SIPM for burst cube. SIPM is short for silicon photomultiplier, and the data, as you can see, is very similar. So that proves that this method works, and it can help us to get on our way for our UVI-GREAT mission. At the end of my presentation, I also tried to do cesium 137 quickly. It's probably not as accurate as it could be, but it goes to show that when you compare them together, they are fairly similar. This is a picture I thought I could have just inputted for fun. This is readout from REVAN. It gives you the number of events, the number of triggered events that were not placed, a lot of different information you can get from REVAN. And finally, I have my future work. I want to be able to simulate other radioactive sources like cobalt-60 and americium-241, as well as determine the energy resolution as a function of energy. I would also like to start simulating real sources like the crab pulsar and evaluate the effective area of the UVI-GREAT instrument. Thank you, and that is the end of my presentation.